All right. Welcome, everyone. We are so very glad that you are here for this month's episode of our Wednesday webinars. We have a great crowd today and a ton more that are registered that'll watch later. Today, we're going to be hearing from Dr. Jake as he shares about how to incorporate robotics into the high school STEM classroom. Specifically, he's going to be telling you about our brand new release of our high school course, Foundations of Engineering, Technology, and Robotics, featuring the Dobot robotic arm. But before we get there, I just want to share with you our upcoming webinar schedule. We have 2 more webinars this school year. In May, our professional learning specialist, Shantae, will be sharing about the importance of failure in STEM classrooms and how we can use failure to spark innovation and creativity. Then in June, I'll be interviewing tech leader and innovator Dr. Liz Lubeski about her top tech tools from this past school year. So please make sure to join us for those last 2 webinars of the year. And then we'll actually be introducing a new format for the upcoming school year for our webinars. So now to our main event, I'd like to introduce Dr. Jake Roark. He is our curriculum and outreach specialist and resident genius. So Jake, take it away.
Okay, I don't know about the genius part. That's a little too gracious, Corey, but thank you. Hey everybody. So nice to have you all here today. And we are here today to talk about this high school robotics course that I've been working on very diligently over the last few months. So without a further ado, let's go ahead and get started. I'm going to go ahead and share my screen. All righty. So without further ado, the title of our webinar today is Foundations of Engineering, Technology, and Robotics. And so that is the name of the curriculum that I have developed, centered around the Dobot Magician robotic arm. So first off, just a little bit about myself. If you haven't seen me on one of these webinars before or met me in person before, my name is Dr. Jake Roark. I graduated with a Bachelor of Science in Physics and Astronomy from Purdue University in 2012. Graduated with an MA and a PhD in physics from Kent State University in 2018. When I was there, I got a PhD in astrophysics. I studied the interior of neutron stars. If you're familiar with what that is, neutron stars are the dense cores that are left over after a star goes supernova. So I essentially was studying very dense nuclear physics in grad school. And I joined the STEM Education Works team a couple of years ago in January. So I just recently this January, I had my 2-year anniversary as a curriculum and outreach specialist with the team. Excuse me. And I generally have a great passion for taking advanced scientific topics, advanced topics in technology, in engineering and mathematics, all the STEM fields, and making those complex ideas really digestible for the general public. One of the things that I really enjoyed doing when I was in grad school was I ran the planetarium at Kent State. So I had students come in for field trips during the week. I had families come in on the weekends. I loved teaching while I was there, being a TA for labs, recitations, and lectures, things like that. So I've always had a passion for teaching. In grad school, I kind of discovered I didn't really want to become a physics professor like I originally planned. But here I am today, back in the education field, where my heart definitely called me back home to the field of education. So now that you've met me a little bit, let me also introduce my sidekick here, the Dobot Magician. So the Dobot Magician robotic arm is the star of the show when it comes to this new high school robotics curriculum that I've developed. The Dobot Magician, one of the great things about it is that it's pretty versatile in terms of the grades that you can teach with it. You can teach subject matter from all the way starting from elementary school all the way up to high school. Again, the content we'll be going over today is specifically more geared towards high school students. But there's many different types of coding for all that you can do with this thing, with all different learning levels. The Dobot Magician also comes with 5 different end effectors. So the end effectors are, for instance, you can see the claw end effector in this image that you see right there. An end effector is essentially just whatever goes on the end of a robotic arm. It's kind of like, think about it like the robot's hand, the kind of tool that you have installed on it. So the Dobot Magician in particular comes with a claw end effector, as you see in this image. It comes with a suction cup end effector, a pin end effector for writing and drawing. It also comes with a 3D printing end effector, so you can 3D print with it. And it also has a laser engraving end effector, which is pretty cool. So now that I've kind of introduced you to both me and my sidekick, the Dobot, let me sort of bring up, well, why are we using robots to teach computer science and coding in the first place? And I would say that there's three main reasons. Why robots? Well, number one, active engagement. Number two, immediate feedback and iterative learning. And lastly, critical reflection. I'm a big believer in the idea of using physical hardware to teach kids how to program, using that as an aid so that they can actually make sense of what their code is doing and look at the results of their code in three-dimensional space rather than simply looking at their computer screen. So first off, the first factor that I think is really important is active engagement. So these kinds of tools like robotic arms that we see here, they really implement hands-on project-based learning. It's STEM learning disguised as a toy. And this thing really in many ways is a learning tool and a toy at the same time. And it's great for students of all different learning types. Some students learn best from, writing up on the chalkboard or the whiteboard and from textbooks and going to a computer and typing things in. And that's great. And that's how I generally learned when I was in school, high school, graduate school, and all that. But there's a lot of kids out there who really, they thrive in that kind of hands-on environment where they can have hardware that goes along with the process of learning computer science. They really thrive when they are able to actually put their mind to a physical system like the Dobot robotic arm. One of the aspects of the active engagement that I think is really helpful that is brought to the table by using robots in the computer science classroom is code to action visualization, understanding that these certain lines of code here result in certain behaviors in the robotic arm. And it also stimulates critical thinking. So the second main factor that I want to point out as to why robots are so useful in the computer science classroom is that they provide immediate feedback and iterative learning. And I think this is perhaps the most important factor as to why robots are so useful in the computer science classroom. If a student successfully codes a robot to perform a specific task, that's awesome. It builds confidence. It means that they knew what they were doing when they were coding. It affirms their prior learning. That's all great. But I think what's even better is when students fail initially. And the reason why is because having a physical interface in front of a student when they're learning how to program a computer or a robot, it really gives them the ability to actively and effectively learn from their mistakes. They're able to look at their robot. They're able to look at, for instance, the Dobot robotic arm and say, well, at what step did it screw up? At what step did it not do exactly what I wanted it to do? And then from there, they can take that point where it malfunctioned, where it didn't do quite what they wanted it to do, and they can match it up to the part of the code where they will inevitably find their error. And this is a huge part of learning how to code. A huge part of computer science is that process of debugging. Debugging is a good thing, and having especially having a physical robotic arm in front of you when you're teaching this stuff is especially helpful, and it makes that process of learning from students being able to learn from their mistakes much smoother. And it also cuts down on frustration and assists in social emotional learning. So we also have to consider that we want to make sure that our students aren't frustrated too much while they're in this learning process. We want them to be able to benefit from learning from their mistakes. And lastly, the last, I would say, the last factor involved here would be critical reflection. I think having a physical interface, a physical robotic arm in front of a student while they're learning how to code, it encourages critical self-evaluation. It really makes them think to themselves, how did I organize my program? And what factors made my program or setup effective? And notice that I'm bolding the word "my" in those two sentences. in those two questions. And the reason why is because students really get a sense of ownership when they get their hands on something, when they actually build something, when they actually are able to program a robotic arm from the ground up. And this very much gives them a sense of ownership in their work. It also spurs students to expand on their learning. So it makes them think, how could I make this program or setup even better? How could I program things more efficiently, perhaps? How could a similar system be used in a community or in a factory or in a hospital? Really makes them think about how robotic systems like the Dobot robotic arm can be applied to real world situations, like manufacturing. In fact, we actually have a Subaru plant not far from here. We go and visit there every once in a while for work, and you can see robotic arms doing very much the same thing that the students will see in front of them with the Dobot robotic arm happening in real life on the factory floor. So let's jump right into it. So I've kind of explained a little bit why I think it's so important to incorporate physical hardware like robotic arms into the computer science classroom. And so specifically with regards to this curriculum that I've developed, Foundations of Engineering, Technology, and Robotics, the target audience is specifically for high school, grades 9 through 12. The length of this curriculum is a full semester, so that typically means 15 to 17 weeks. And the equipment that will be necessary in order to complete this curriculum is the Dobot Magician robotic arms and the Dobot conveyor belts and sensors. And you can see a quick little image of the Dobot robotic arms and the sensors and conveyor belt system down at the bottom of the screen there. And this curriculum is particularly great for teaching subjects like robotics, for teaching things like computational thinking and computer science, computer programming, both in the form of block coding and Python, problem-solving skills, career and technical education, advanced manufacturing, as well as ethical design in the engineering design process. So we actually have 3 different versions of the packages that you can purchase for this curriculum. The first version that we have here is the Starter Robotics package. In this package, you have 4 Dobot robotic arm systems, as well as 4 Dobot robotic arm units, as well as 2 conveyor belt kits, and then 4 coordinate boards that can be used separately from the conveyor belt kit for the Dobot robotic arms. Those, of course, also come with the books that you see in the class pack. I'll talk about the class pack here in just a second. The second version is the Classroom Robotics package, a little bit larger, where you get 6 Dobot robotic arms and 3 conveyor belt kits. And then lastly, we have the Technology Lab Robotics package. That comes with 12 Dobot robotic arms, as well as 6 conveyor belt sets. You'll notice here that the number of Dobots is always twice the number of conveyor belts, and that allows you to do the setup that you see in the slide here, where you can have 2 robotic arms, 2 Dobot Magicians working on the same conveyor belt system. So this is now that we talked a little bit about those different packages, going back to that class pack there, what comes in that box that says class pack is contents like this here. So we have activity and reference books. This is essentially a booklet full of worksheets and reference material for your students to go through while they're reviewing this curriculum. We also have some Dobot dollars down at the bottom there. Those are for a project where the students are going to be programming their Dobot to act like an ATM. We also have some rectangular blocks. 30 of those are included in the class pack. We also have a series of a bunch of these foam square blocks that also come as a part of the conveyor belt kits. And we also have the glasses at the bottom, the protective glasses. Those are specifically used when you're using the laser engraver end effector of the Dobot robotic arm. You also have 100 wood planks that are about the size of a coaster. Those are also used in conjunction with the laser engraving end effector. You have 60 of these X and O cards that you see right there in the middle. That's for when the students will be programming their Dobots to play tic-tac-toe with them. And then up at the very top right corner here, we have some cutlery cutouts, and that's going to be for a teaching and playback project where the students are they're going to enter a scenario in which they're helping a neighbor who's physically disabled, and they're going to be teaching their Dobot how to set the table for their neighbor. And so Now let's jump into a little bit of the structure of the curriculum. So the unit 1 starts off with the introduction to robotics. In this first unit, students are going to be learning what exactly is a robot, what is the modern state of robotics as a field today, what are the major parts of a robot. They're going to be learning a little bit about systems thinking and breaking processes down into inputs, outputs, and processes. And they're also going to be learning how to use flowcharts to model more complex nonlinear processes. And flowcharts are going to become a very important thing in this curriculum later on. You'll see drawing up flowcharts is a really great way to get students to think critically about the structure of their computer programs. In Unit 2, they're going to be learning about block coding and computational thinking. In this second unit here, they're going to get their first real taste of actually, programming, building their first computer program to control their Dobot robotic arm. They're going to learn a little bit about variables and lists. And then they're going to, in the third lesson in Unit 2, they're going to learn about dynamic programming, specifically logic, loops, and functions. And if any of you out there are computer science teachers, you'll know that when it comes to computer programming, at the end of the day, variables, lists, logic, loops, and functions, those are the most important aspects. Understanding and mastering those tools are incredibly important when it comes to learning how to program a computer or a robot. Next in Unit 3, we have text coding and computer science. So in this unit, the students are first going to be learning how to transition from block coding, a simplified version of coding that we'll take a little look at here a little later. And they're actually going to be entering into the world of text-based coding, specifically Python. In this unit, they're going to be learning about inputs and outputs and how they correspond to variables and lists in Python. And then finally, they're going to finish off this unit by learning about dynamic programming in Python, specifically logic, loops, and functions in the context of text-based coding. In Unit 4, we are diving into the subject of advanced manufacturing. In this unit, we're learning about very important concepts in advanced manufacturing, like efficient production, intelligent production and quality control, and effective organization. This is going to be the first unit in which the students are going to be diving in and using the conveyor belt kits in conjunction with their Dobot robotic arms. And then lastly, in Unit 5, the students are going to be learning about robotics and society. So they're going to be learning about how robots are used to save people's lives in disaster situations. There's a really cool project in that unit where basically the students are going to be learning how to attach the color sensor to the end of their Dobot robotic arm and treat it like it is a rescue helicopter out on the ocean. And they're going to rescue all of the cubes that are red, because that's the color of the people's life jackets, and they're going to ignore the green and blue blocks. So they're going to program the robotic arm to save all of the people who are in need of rescuing in like a Coast Guard rescue situation, but ignore all of the debris that's in the ocean. In this unit, they're learning, again, they learn about how robots are used in disaster situations. They're learning about robots and ethics, what it means to ethically program and design something, and how the program and design of something can affect individuals and society as a whole. And then lastly, they will be applying everything they've learned up to this point in the engineering design process. In this final lesson of the curriculum, they will be completing their own capstone project where they will be designing an object that can be used in conjunction with the Dobot to solve a certain problem. And so really, the main structure of this curriculum is to transition students from very basic coding all the way to the point where they are able to learn how to code in Python. So we're starting them off with things like teaching and playback type coding. That's when you move the robotic arm around, tell the robotic arm to turn on its suction cup end effector, turn off the suction cup end effector, and then you press a button and it will replay everything that the students just played out with the arm. A very, very basic form of coding with just a linear set of steps. Another very basic form of coding that they're going to do is using the writing and drawing lab in Dobot Lab, which we'll talk about a little bit later. So from there, they're going to transition from those very basic forms of coding, and then they're going to code in Dobot Block Lab. So that's the block coding portion of the curriculum. And then finally, they transition from block coding to coding in Python. So this curriculum is standards aligned. We want to make sure that it is, that the content of this curriculum is very much aligned with the major standards that are used. So for instance, we have Common Core, we have Next Generation Science Standards, ITEA, actually just recently got back from an ITEA conference, very fun, ISTE standards, and CSTA. And we give you for each unit and each individual lesson which standards apply to each. And so now I'm going to talk a little bit about the 5E model. We use the 5E model in all of our curriculum. We're a big believer that this is a really, really great way to get students engaged and to explore the content within each lesson. So the 5 steps in the 5E model are engage, explore, explain, engineer, and evaluate. And at this point, I'm actually going to go ahead and I'm actually going to show you an example of one of our lessons and how the 5E model fits in there. So this is a PDF version of the curriculum, Foundation of Engineering, Technology, and Robotics. So first off, let's scroll down a little bit. We have the table of contents, of course, for the curriculum content. We have a curriculum guide for you, talk about the standards, go down a little bit further. And so this right here is an overview for Unit 1. Each unit starts off with a description of the unit. We have a cultural connections section. Basically, this draws connections between the content that the students are going to experience in that unit and how that applies to the world around them. We also have a career connections section here where the students learn about what kind of careers correspond to the content in that unit coming up. We also have an engagement method for each unit. So these are methods, ways of getting students more engaged with the content. For instance, for this first unit here, we suggest using sticky notes as a way to sort of collect and brainstorm ideas for classroom discussions. And of course, we have the standards for each lesson throughout that unit, the unit. And so here we go. Lesson 1, what is a robot? We always start off with a general overview here. And then we have all of the standards that apply to Unit 1, Lesson 1 that we're looking at right now. We have enduring understandings, driving questions, learning objectives, the required instructor preparation, the materials that you will need to complete this particular lesson, instructor resources, student resources, and vocabulary that applies to this lesson. And so the lesson always starts off with an engage activity. Of course, that's the first E in the 5E model. And so specifically in this case, the students will start off by going through some content in a slideshow. So for instance, this is the slideshow here for Unit 1, Lesson 1. And so they're learning about those cultural connections and career connections. They're learning about how to operate the Dobot Magician. They're learning about the history of robotics. Then they're getting into what is a robot, what makes a robot, how is it different from something like a machine or a tool, the components of a robot, so on and so forth. So it's very common in this curriculum that students will be using a lot of content from the slideshows that we've put together for you. Additionally, in this engage section, we also have a worksheet that we have the students do afterwards. So after they go through and complete the engage section, they're going to go down to the explore section. So again, the engage step is meant to capture the students' imagination, get their attention, and prepare them for what they're about to learn. In the explore section, this is the time to literally just let them explore, let them gain some knowledge for themselves. You're not quite explaining or teaching or giving them the concepts just yet. You're just letting them put out their feelers and get an idea for the subject content for that lesson. And specifically, for this explore section, we have the students filling out this worksheet here called Unpacking Your Dobot. And basically what the students are doing is they're taking out all of the components of their Dobot Magician robotic arms and learning what each part is. So here they're taking out some end effectors. We have a vacuum pump, pin holder, the laser end effector, power cord, 3D printer kit, USB cable, motors, so on and so forth. And throughout that worksheet, they're trying to identify, okay, well, we went over what the different parts of a robot are. And now they're trying to identify, well, this particular part, what category does it fit under? Is it an actuator? Is it an end effector? Is it a control system? So on and so forth. So that takes care of engage and explore. Next, in the explain section, this is typically the content here in the explain section is, of course, you're explaining some content to them. This is when you're really getting into the meat and cheese of the teaching portion of the lesson. Specifically, in this case, we have them learning how to use the writing and drawing lab via the slideshow I showed you previously. And then in the engineer section, this is actually where when the kids actually get a chance to actually get their hands on some physical system that they're working with. So specifically for this engineer section, what the students are doing is they're getting the chance to complete the autograph project. And the autograph project is right here. So the problem, you are a world famous robotics engineer. Today, you're attending a prestigious STEM conference where you will be signing hundreds of autographs. Oh boy, there's just one problem. Your writing hand is very sore from shredding your guitar at a concert the previous night. Did I mention you're also a rock star in this parallel universe we have right here? So their challenge is to set up their Dobot Magician with the pin and effector and teach their Dobot how to write their names using the writing and drawing lab and Dobot lab. And again, one of the big components of this curriculum is we encourage the students and the instructors to have their students construct a digital design journal throughout the process of this curriculum. Basically, all that is a PowerPoint presentation that the students can use that essentially acts as almost like a lab notebook. So in the same way that a scientist or an engineer, when they're doing their work, they are going to have a big notebook with graph paper in it, and they're going to be writing in pen, and that's how they record all of their progress through a project. In very much the same way that a professional scientist or engineer would use a lab notebook, the students are going to be using that digital design journal, that PowerPoint file, to record their progress throughout the course of the curriculum. And this digital design journal is going to be the basis upon which the teachers, the instructor is going to grade the students' work. So that's the autograph project there. And then lastly, the last step, evaluate. The students are again evaluating what they've learned so far. They're addressing what things they understood well, what things they might have not understood so well, and specifically in this case, they're reviewing some reflection questions from the autograph project. And so that basically gives you an idea of the general structure of the curriculum and how it follows the 5E model. Next, let's go ahead, jump back into the slideshow here. I would like to point out here that this is Dobot Lab. Dobot Lab is the interface that you'll be using in order to control the Dobot Magician robotic arm. And of course, we have several different interfaces here, different modules that you can use to control the Dobot robotic arm. You have Dobot Block Lab that uses block coding. You have Python Lab, which of course uses Python. You have the Writing and Drawing Lab, which I just described earlier. You have the laser engraving lab, very similar to the writing and drawing lab, except you're using the laser engraver to engrave on things like wood or acrylic. You have the teaching and playback lab. For those who are not familiar, again, like I mentioned that before in a previous slide, teaching and playback is essentially a very simple form of coding in which the students are performing a certain set of actions on the Dobot and then pressing a play button, and it's going to repeat everything they did with the Dobot. And of course, a 3D printing lab. So students are typically, if you're trying to work your students up to be able to program in Python, you're usually going to start off with something like teaching and playback lab, then transition into block coding, and then transition into text-based coding, specifically Python. So again, here's a little image of what the teaching and playback lab looks like. Again, very simple linear steps. Then next, when you go into Dobot Block Lab, the block coding, again, it's a little bit more complex, but if any of you have familiar with coding and things like Scratch, if you've used one form of block coding, you've pretty much used them all, because block coding is meant to be very simple, intuitive, and based on visual learning. And then lastly, students will make their way into coding in Python. And so right now, what I'm going to do is I'm going to show you guys a quick example of a kind of project that the students will be performing in later on in the course. This is the quality control project. This is specifically from Unit 4, Lesson 2. So this is the advanced manufacturing unit. And so basically what the students are doing is they are being tasked with programming their Dobot and conveyor belt system to sort through colored blocks, and any of the blocks that are green need to be discarded. So, the scenario here is you work for a company that manufactures red and blue blocks. Unfortunately, a batch has turned out green because someone mixed the paint pigments incorrectly. You've been tasked with creating a program in Python that uses a Dobot, a conveyor belt, a photoelectric sensor, and a color sensor to pull these faulty green blocks out of your production process. So I'm going to go ahead and exit out of that for now, and I'm going to jump right in here to my block coding program. Now, granted, by the time the students get to advanced manufacturing, the 4th unit of this curriculum, they'll actually be programming in Python, but I thought I'd start off by showing you guys what this would generally look like in block code format first, just to keep things simple initially. So next, what I'm going to do, I'm actually going to go back to my Zoom screen. I'm going to stop sharing for a second, and I'm going to switch my cameras. I'm going to make sure that you guys can see the Dobot system that I have in front of me right here. So I'm going to adjust it a little bit. Here we go. I'm going to go back just a tad, just so you get a full view. There we go. Beautiful. Okay, so this is our Dobot hooked up to our conveyor belt system. We have our Dobot robotic arm right here. Say hi, Dobot. Thank you, Dobot. Here's our conveyor belt. Here's our photoelectric sensor that can sense if something moves in front of it. And here is our color sensor. This is going to be our discard pile for our green blocks, and our red and blue blocks are just going to fall off the conveyor belt here and continue on in our production process. So now I'm going to go ahead, I'm going to share my screen one more time. So we're running our system, and I'm going to go ahead and I'm going to place a red block on the conveyor belt here. The Dobot is going to sense via that photoelectric sensor that something passed in front of it, stops the conveyor belt, picks it up. It's going to put it over our color sensor, and it says, aha, that block is not green. It is either red or blue. It's going to put it back on our conveyor belt, and our conveyor belt's going to continue to go there. I'm going to put a blue block on, and I'm going to see if it works for blue. Again, it should check the block. It should detect correctly that it's not green. So this right here on our screen, we're up in the upper right-hand corner where it says color sensor status. It should stay not green. Very good. I'm going to put it back on our conveyor belt, and it's going to continue on. Now I'm going to throw a little bit of a monkey wrench into the system, and I put a green block on our conveyor belt. So now it's going to go do the same thing. It's going to pick up our green block. It's going to move it over to our color sensor. And aha, it changed to green. And so now it is going to go ahead and drop it into our discard little cup there. So generally speaking, what's happening here is first we're setting the jump height for the jump maneuver. Basically, this tells the Dobot how high to lift its arm when it's moving from one point to another. This right here on our screen, Corey, you're able to see my mouse as I move it across the screen?
Yep.
Fantastic. This jump to block here is telling it to go to its home position. Then we're telling the conveyor belt to turn on and go at a certain speed. Then we're initializing our infrared sensor, our photoelectric sensor, and our color sensor. And we're setting its values to blank values at first. And then we have a block here that says repeat forever. So this is a infinite while loop. And so if our infrared sensor, if its value is 1, if you're familiar with computer programming, typically 0 means off, 1 means on. So if our photoelectric sensor switches over to a status of 1, then we're going to set our photoelectric sensor status variable to on. And then we're going to go to this function called check color function. From that point, our program is going to go up to here. And in fact, you can see that happening in live action. Whatever part of our block program is highlighted There we go. So now it's going to that function. It's stopping our conveyor belt. It's going to that position to pick up the block, turning on the suction cup. This is the color checking location that it's at right now. And so I wait 2 seconds so it can get a good reading on what color that block is. And then we have an if statement here. So you know how we talked about variables and lists. So we've already used some variables so far in this block program. We already see a loop over here. We have a repeat forever loop. And then we have a conditional statement here. So a logic statement. So if, and we also have a function right here, this define check color function. So as you can see, underneath that wait 2 seconds, after we get a good reading on the color of the block, we're going to go ahead and check and see if what the color sensor status is. If the color sensor status is green, then we're going to drop it off at the cup. That's this location right here, this set of coordinates. And of course, otherwise, we're going to set the color sensor status to not green. And that means that we're going to put it back on our conveyor belt right here, turn the suction cup off and let it go. And then, of course, after we're done with that process, we're going back to the default position and turning our conveyor belt back on. Now, I'm going to switch over real quick. I'm going to show you that we can do that exact same thing, but with Python. So basically, this is an identical program where we're using Python. Obviously, here you can see that there's a lot of syntax. That's kind of the grammar of a text-based coding language like Python. So we see a lot of colons, semicolons. We see a lot of parentheses. We see a lot of code words like def and if. This is the syntax that makes learning a text-based programming language a little difficult at first. And that's why learning via block coding first to understand those concepts is really nice. You don't have to work, the students will not have to work their way through learning all of this syntax right away. But as you can see, basically the structure of our program is exactly the same. We're setting our parameters here, initializing our variables and our functions. We're defining our check color function right here. We have an if statement right here, an if else statement. So again, that's more logic. And again, down here, we're going back to our home position after we check the color of our block. We're turning our conveyor belt back on. And this is actually the main portion of our code. Our code actually starts down here. So we have a forever loop here. So while true, this is a forever loop that's going to go on and on and on until we click stop program. So again, we're initializing the value of our photoelectric sensor variable. That's our variable right here. We're checking what its value is, if it's 1 or 0. And if it is 1, we're going to go ahead and check the color of our block. And so let's go ahead. I'm going to touch that right there and shut off my program there so that it is no longer making any noise. And so, yeah, so with that, that is the gist of the curriculum that I developed. I'm very happy about this curriculum. It took a while to put it together, but it's very much complete. Had to kind of go back and teach myself how to code in some Python here and there, actually. So that was actually pretty fun. But yeah, so this curriculum is very much based around a high school robotics curriculum. Can last up to a semester. You technically could use little pieces of it if you did not necessarily want to go through the whole semester. You also have the option, if your high school students in your class are already familiar with block coding, that you do have the option of having them code in Python from the very beginning. So with that, if we have any questions, feel free to ask. But thank you guys very much for your time.
And if you are interested in getting a better view of the curriculum, we can definitely give you access to some samples of the curriculum. So feel free to reach out to one of us. Actually, you can reach out to the whole team. We're at learn@stemeducationworks.com. I'm going to go ahead and put that in the chat for everybody. If you wanted to just shoot us an email, we'll give you access to a sample of the curriculum, of the foundations of engineering, technology, and robotics curriculum. All right, well, we will be sending out a recording of this webinar probably tomorrow, so be looking for that. And then again, we want to make sure that you know about the upcoming webinars. Next month will again be Shantae talking about the importance of failure in STEM classrooms. And the following month, we'll be looking at ed tech tools from this school year. So look for those invitations, usually the first week of each month. And with that, we just want to say again, thank you so much for coming. We were so glad you are here, and feel free to reach out with any questions. Have a great day.
Thank you all very much.